I'm Maximilian and Rasmus and Konrad, and we want to tell you the story how we got lost in translation and found our way back embracing Rust and with type-safe coordinate systems. First, a few words on who we are. We are a RoboCup team of students and robotics enthusiasts from Hamburg University of Technology in Germany, and we are doing autonomous robot soccer, and that since 2013. We do that in our free time, all while doing open source contributions, publishing our own releases of software, and also publishing our scientific results in form of research papers. Most importantly, we are the first RoboCup team to seriously integrate Rust into our robot control. So what is RoboCup? RoboCup is an international competition where robots play soccer autonomously. That means actually robots kicking the ball, running over the field, scoring goals, and whatnot. In our division, the Standard Platform League, or in short SPL, all teams use the exact same identical hardware. So our focus is mostly on software engineering and communication issues, teamwork, perception, modeling, planning, and also motion control. To sum it up, we are doing real-time robotics under physical, strategic, and computational constraints. I mentioned Rust, so where do we use Rust? Actually, nowadays we use Rust all over the place. So we start on the bottom with our custom Yocto Linux. We built for the now platform for this robot, which delivers us an SDK with cross-compilers targeting the platform, a cargo to actually compile and everything. On top of that runs our custom robot control framework that involves tasks to actually make the robot play soccer. That means perception, like seeing the ball in an image, seeing field marks in the field, seeing other robots, maybe even teammates, doing sensor fusion, like, for example, providing localization of answering the question, where is the robot in the current moment of time, or fusing the IMU to know where it is placed in the world. Doing behavior, so managing 7 robots on the field, playing against 7 other robots in the field to actually do something useful. And that's not that easy. And finally, motion control, which, for example, just means walking, so getting from A to B, which is also extremely difficult on 2 legs. And, for example, also getting up if the robot is falling down, because as they do it autonomously, we can't help them, they have to do it on their own. On our side, so on our local machines, we run Rust-based tooling. So we have a live connection via Ethernet or Wi-Fi to the robot via WebSockets, for example, to live visualize the current state of the robot, like where it sees the ball, for example, where it thinks it is. We are also capable of recording the entire state of an entire match to the robot's disk and replaying it afterwards, so we can revisit and step through and find what actual bug led to us losing a last match, for example. And we also developed our own simulation framework environment, for example, for behavior simulations based on the Bevy engine, which we use also in CI to continuously check whether our robot's behavior is still able to score goals if I just change a little line in the keeper behavior and suddenly the striker doesn't score goals anymore. I want now to give you an impression of what we do on a daily basis, and I prepared a video for that, and we switch over to that and enjoy a video for a moment. okay. Thank you. That's the next YouTube video. Let's dive deeper into the topic we brought to you today. I want you to meet Alice and Alice's friend Bob. Alice and Bob are robots in our soccer field, and as they play soccer autonomously, they have to communicate with each other. They have to communicate what they see, what they want, or in general, they will have to share state between different robots. So let's assume Alice wants to tell Bob the location of the ball. So Alice sends a message to Bob telling, I saw the ball at point to x coordinate 3.0, y coordinate 2.0. And Bob received that message and thinks, neat, I have a function to walk to a specific position, so I can walk for the ball. Let's take the ball from Alice and pass it to the function and start walking. And, Alice is confused. What's Bob doing? Like he wanted to head for the ball. Bob himself is confused. That is not where he intended to end up. What happened? Turns out Bob and Alice were talking about different coordinate reference frames. Depending on where you place your origin of your reference frame, makes coordinates mean completely different things. It depends on how you line up your coordinate system. So to sum it up, coordinates alone are not enough. We are missing the frame of reference. Okay, let's dream about a solution to our problem. We need something that prevents Alice and Bob bugs. That means ensuring that we are talking about the same frame of reference. We want something that allows safe and easy frame conversion. So if we want to talk about different frames, we have to converse with each other. We want to have that checked at compile time, because all necessary information we have available at compile time before uploading to the robot at runtime. We want to have it zero cost. We don't want to pay any additional overhead for that. And in the best case, also have it self-documenting the frames we need to the user using our APIs, our functions, and like playing around with the variables at hand. So how can we achieve that?
Right, thank you, Maxi. So how might we solve a problem like this? So imagine we have a point defined like so as a struct. How might we now add frame information to this struct? Like one example, we could add another field to the struct containing a frame, which is an enum. So we could check this enum at runtime and see if the frames match, for example. But this is not zero cost, because we have to actually store this. It takes up memory, and the checks do not happen at compile time. So this is not what we want. We could also use the type system to differentiate between different points. So we could have a point type for a point relative to the world and a point relative to the robot, but this is really tedious and does not scale well. So what can we do instead? What we really want is to have a point which is generic over the frame that it is relative to. So we want to write something like this, but at the moment this won't compile, because the Rust compiler wants to have a field in the struct that actually uses this generic parameter. And most of you probably already know what to do in this situation, but for those of you who don't, there's something in the Rust standard library that we can use in this case, which is phantom data, which is a zero-size type, so it doesn't take up any space in memory. It also doesn't add any overhead at runtime, and we can use it to associate or to tag, so to say, our struct with a certain type, even though it doesn't really depend on it. So how would this look in practice? We have our point struct like before, and we can rewrite it like so to be generic over the frame. Now, you're all familiar with the concept of type safety and memory safety, but right now with this concept, we gained another type of safety from the Rust compiler, and we might call this something like frame safety, for example. Now, back to Alice and Bob. How would this look in practice? When Alice constructs this ball variable, she needs to specify, using our new point that we defined earlier, the frame of reference. In this case, we can just insert anything into the generic parameter, but unit structs work very well because we can give them names. and reference them across crates. So we specify that this point is relative to the world coordinate system, like so. Now we send this ball off to Bob, and Bob has a walk-to-point function. And when writing this function, we can specify in the function signature that we expect a point that is relative to the current robot position. Because as we saw before, when we told Bob to go to point 3,2, that was relative to the robot. Now, this wouldn't compile at the moment, and this is why. Oh, hold on. What's going on? Back to the code. I think we forgot a semicolon. Now, this is the real compiler error. In this case, the compiler is really helpful because it tells us that we used a point that is in the wrong frame of reference, and it tells us what it expected. So we need to put in a point that is relative to the robot frame of reference, and we put in a point in world coordinates. So that's cool, but how do we move from one frame of reference to another? So linear algebra has something for this. It's called an isometry, and it works by first rotating our entire frame of reference about the origin by some angle, and then offsetting the entire plane by some amount x and y. So we can use this to transform from our robot coordinate system to our world coordinate system, for example. Now, in this case, the isometry doesn't have any idea what it's transforming from or to, but we can also add this with generic parameters like so. And now the isometry is also frame safe. We added 2 generic parameters, from and to, and now just by looking at it, you know what this isometry is transforming from and where it's transforming to. The magic happens in the implementation. We implement the mold trait from the standard library for our isometry in such a way that it only accepts a point from its from type, or from the from frame of reference, and we define it so that the output of this multiplication is a point in another frame of reference, so it produces a different type entirely. These two are not compatible anymore. Back to Alice and Bob. So we receive, or on Alice's side, we receive this, on Bob's side, we receive this point from Alice, and we know it's in world coordinates, and we also have this world-to-robot isometry. We gain that from our localization, so the robot knows where it is roughly in the field, and this is stored as an isometry. We can now multiply these two together to get the ball position in the robot frame of reference. And we can now put it into a walk-to-point function, and it works just fine. If we would use the wrong frames, for example, in this case, we switched up robot and world in our isometry, so this is the same isometry backwards, the other way around. If we try to multiply these two together, the compiler is also very helpful, and it tells us that this multiplication expected a point in robot coordinates, but we gave it one in relative to world. Now, this is cool, but we're still missing a lot to turn this into a complete solution, and Konrad is going to tell you more about this.
Yes, thank you. So linear algebra is more than just points. We also have vectors, planes, hyperplanes, translations, rotations, reflections, scaling, and so much more. And we actually use most of these things in our robotics code. Luckily, we don't need to implement this ourselves. If we look on crates.io, we can find libraries like Nalgebra, which is the most popular linear algebra library on crates.io, and it has good documentation and community support. It implements most of the things that we need, but now how can we combine this with our frame idea? So we are wrapping algebra effectively. We have this framed type instead of the point type that you saw earlier, and this is generic over 2 types. One, the frame, and then the inner type. And this frame type is intended to wrap algebra types that exist within a coordinate system. So that is points, vectors, orientations, stuff like that. The Rust compiler will likely make this type the same size as the inner type, but we can also add this representation attribute with transparent to have the compiler guarantee that it's actually the same size, making it zero cost in terms of memory. And then we also provide some aliases so that the users can stick to the same named types as they're used to from algebra. So we define our own point2 with the wrapped point2 type from algebra. So what this actually look like? This is a small piece of code which currently uses the algebra point2 type. And you can see that in the signature of these two functions. Now, to convert this to our system, you basically don't have to change almost anything. Instead of importing the algebra type, you import the other type, and then you define the coordinate systems as just a unit struct. And then all you have to do is add the coordinate systems to the point types in the signature. And yeah, that's basically it. When applying this to our code base, like our whole robotics domain code base, we actually spend a lot more time trying to figure out what the correct coordinate system is than actually making the change in the code. And we do the same for transforms, such as the isometry. These take 2 frames and an inner type, and use the same phantom data trick to get the from and to types in there. We also use the transparent representation, and then we also have the type aliases to get the familiar types and type names in there. So we actually have a lot of frames in our robotics code. This is just an excerpt from a crate that we have, whose whole job it is to define these types. In this one file, we have 37 different coordinate systems. That may sound like a lot, but if you look at the robot, each single joint here has its own coordinate system. So there's one for the right foot, one for the right upper arm, lower arm, hand, head, body. So that adds up quickly. We also have coordinate systems for the cameras and also more like virtual coordinate systems that don't exist physically for image positions, for example. All of these coordinate systems have doc comments pointing out what they are intended to be used for, where the origin is, how they are oriented, and that makes it very easy to, if you look at these code examples, if you have this open in your IDE, you can just hover over the world type and get all of this information. Now, let's move on to a real-world example, how this would look like in our code base. Here we have a function from our debug visualization for the walking engine. And I'm going to step through this, kind of explaining what these things do. Don't try to understand what the function does, because it's kind of complicated. I will try to focus on the linear algebra part. So first, it takes a painter, which is actually an eGUI thing, which we use for, well, painting. And you notice this type is actually also generic over the reference frame. That's because we have different painters, for example, for painting stuff relative to a robot or within a rendered image from the camera. And this painter only accepts positions within that coordinate frame. So we can't accidentally pass a pixel position to something that paints on the floor. Now, this function also takes some isometries. These are 3-dimensional, unlike the 2-dimensional ones we saw before. And these are all transformations from different other frames to the robot frame. The other way around. And then we also take some poses, which are similar to isometries, but they only have one coordinate system associated with them. So they are a position and orientation within a coordinate system, but don't create a new coordinate system at that location. Now, I misspoke earlier. That's because we are actually interested in the walk-to-robot transformation and not the robot-to-walk. So we can just call the inverse function on this, which returns a new isometry with the mathematics inverted, but also the frames flipped. So if we multiply a point to this, this actually translates from the walk coordinate system to the robot coordinate system instead of the other way around. And there's no way of messing this up, really. Like, you call the inverse function, and then you get an isometry that's the other way around. You can't accidentally multiply a point in robot to the walk-to-robot isometry. Now, as I alluded to earlier, the poses are very similar to isometries, but they don't create a new coordinate system at that location. But sometimes we want that. So in this case, we take a pose 3 and call the as-transform function and convert this to an isometry with a new coordinate system that we define in place within this function, and then we invert it. So in this case, we need to specify the coordinate system that we want to use for the as-transform, but that's not always the case, because in many cases, the compiler can actually figure out what the other coordinate system is, just based on how this type is used. So here we can see that we multiply the end swing sole at the very right, which is a pose with the upcoming walk to support sole isometry, and then with the support sole as transform, which is then also an isometry. And then we end up with a pose 3 in the robot coordinate system, because that is what the support sole as transform isometry outputs. And if you were to switch any of these around, it wouldn't work anymore, it wouldn't compile. So this is really nice when either modifying the code or writing new code, maintaining, refactoring. Yeah, and then at the very end, we can transform this from robot to, from the walk coordinate system to the robot coordinate system to the ground coordinate system. And finally, we have something in the ground coordinate system that we can pass to our painter.
Okay, let's wrap this up. We wanted to have something that prevents Alice and Bob bugs. So talking about the same frame of reference, we did. We wanted to have something to allow safe and easy frame conversion. Rasmus explained that is possible. We have that checked at compile time. The compiler explains and complains. We have it zero cost thanks to the phantom data. And we also have it self-documenting the frames at the function signature, so our users can just see what they need to pass to the function. And with that, I finish our talk. I've brought some further resources, our website where you can find all the things we publish, including our source code, for example, our slides, which are publicly available, our YouTube, where you can find more of these cool videos I showed earlier, and our Instagram, where we try to keep the public up to date on what we do every day. And with that, special thanks to sponsors that they make that actually happen. Also, shout out to KDAB that makes, for example, us existing. So special thanks to you, and thanks for you for listening. Thank you very much.
Do we have any questions? Was anything lost in translation for the audience from this talk? I think there's one back here, right? Yeah, I got it. And here. Was there any? Yes, Leon.
So having played a few times with OpenGL, I can absolutely relate to this problem. Is this available in a crate somewhere that I can use for example, OpenGL programming?
Currently, it's just part of our monorepo, but we are working on that, maybe on the train home or something.
Did I see two hands?
Also, if you have a special name suggestion, we are still open for discussion because linear algebra is still overused, already overused.
Okay, I'm going to come here, here, and there.
Very interesting presentation, first of all. Thank you. Did you notice any, or do you expect to notice any problems with, for example, compile times? Because yeah, I'm not sure if Rust will actually optimize it before, like after monomorphization, where I just realize, okay, I'm just compiling the same function 5, or if it gets more complicated, 25 times. What?
I actually don't know. Probably it doesn't. We have huge issues with compile time anyway. So currently it doesn't seem to be an issue. We split a lot of robotics domain into different crates to not have them recompile everything, because usually you set our system up once on your local machine, then it compiles actually for minutes for the first time, and then it's incremental recompilation, which works quite well because on the internals of coordinate systems and stuff, you usually don't change much. If you introduce a local coordinate system that's just scoped for this function, then it should be fine. But there's actually definitely overhead for that. I have no measurements on that, how much it is, but it is a problem.
Great presentation. I think it demonstrates how things should be architected in Rust application. But the question, and hopefully it doesn't sound anywhere offensive, did you learn Rust yourself on your own? Did you have it as a university course, or did you have the support from one of your sponsors on your learning journey?
We are all self-taught. University teaches C in first semester, and in the newest edition with some new junior professors now Python. So we ditched Java. But we are not teaching Rust. Like in the university, it's not taught. Us now doing our code base on Rust since 21, I think, ish, maybe end of 20. We have some experience in the team, but students are also leaving and new ones are coming. So we invented our own teaching curriculum for them to join our team. We usually, when the semester starts, we invite new people and we do 1 weekend of crash course in Rust, and then we just pair a lot and try to convey stuff. And usually we try to target early semesters, so bachelors mostly, because then we have the longest time with them. And these are usually not spoiled yet with some C++ idiomatic things, so it actually is quite fun to teach them the idiomatic Rust stuff, but everything is self-taught, yeah.
Okay. And one more question here.
Yeah, that's a very interesting talk and a good demonstration of typing, I think it's called, basically adding semantics to types transparently. Have you tried UOM, which is unit of measures?
Yes. So we know that it exists, and it does basically the same thing for units. Yes, it's the same pattern. I don't think we use it in our robotics code at the moment, but we're aware of it, and we certainly didn't invent the pattern.
Yeah. Like in our code base, everything is SR units, so we not so much have a problem of that, but yeah, there's other things using the same pattern, which is really nice.
All right, thank you so much, Maximilian, Rasmus, and Konrad. And is this Hans-Dieter who's... Hans-Dieter. So standing here, he's looking very longingly at the ball, I feel like. I don't know, he's a little bit like, let me kick it. But he has to behave. Yeah, so...